So we have the angles of the incident and the reflected and the transmitted, but we really want the amplitudes and the phases. And for those, we have to look more at electromagnetism. So what we're going to do is get boundary conditions on the electric and magnetic fields from Maxwell's equations. Now, in a full treatment of this would really be something in an electromagnetism course. And you would do all 4 Maxwell's equations and get all kinds of boundary conditions. We're just going to quickly do the 2 you need to get the reflection coefficients and the transmission coefficients. So this is sort of a quick mini version of this because I don't want to get real deep in it. Okay? So let's just remember that we are at a dielectric interface and we're thinking about an electromagnetic field coming in, and it might be polarized like this, or the E field looks like that, going sinusoidal, or it might be coming in with the E field going sort of out of the board and into the board, etc. But really, it doesn't matter. For what we're about to derive, it doesn't matter which way the electric field is pointing. It doesn't even have to be an electromagnetic plane wave. What we're deriving is really just the electric field, how it behaves at an interface. So what we're going to do is we're going to use Faraday's law of induction, one of the 4 Maxwell's equations. And we know that it's the integral around a loop of E dot dl has to equal minus the time derivative ddt of the integral of B dot dA. So in Faraday's experiment, this was changing the magnetic, moving a magnet near a loop, and this was getting an EMF from that changing magnetic flux in the loop. So if we were going to apply that to one of these interfaces here with the electric fields and be thinking about it, you make your loop, imagine making a loop like this with some length L on this side and some length, say, delta Y on that side. And you'd say, well, what's it going to be? Well, we have the E field is going to have some component, no matter what it is, electromagnetic plane wave, arbitrary E field, it's going to have a component E tangential, and it's going to have a component E perpendicular. Right? Those are both going to be there. Whatever you've got, you can break it into those 2 components. So then, as you go around here, you're just walking around E, little E dot ds's or E dot dl's as you go around. So it would basically be, if we do something really small where the E field isn't changing, it'd be the E tangential part times this length L as you go here. And then as you go down, it'd be, in this case, let's see, the E, if we assume it's pointing up and we're moving down, it would be minus E perpendicular times delta Y. Then as you come this way, you'll notice if we assume the E tangential is this way and we walk this way along L, that would be negative minus E tangential L. And as we go up, we're going with delta Y plus E perpendicular delta Y. And that all has to equal whatever B dot dA is. Right? So that would be d dt of B. And then you could say, well, in the small limit, B is constant, and it's just L times delta Y. So you sort of think of things like this. But what we're trying to figure out is really the E field right at the surface. So you do this trick where you shrink delta Y to 0. This has to be true for any size of this path, so we can make the path basically infinitely thin. And if you shrink delta Y to 0, that goes to 0, that goes to 0, and the area goes to 0. Right? So really all you're left with is that E tangential, and I should put outside here, has to be equal, or times L, has to be equal to E tangential inside times L. And of course the L's cancel. So what you find is that the tangential component of the electric field across a boundary is continuous. Okay? The entire field is not continuous. We could do other laws to show what happens with the perpendicular component, but E tangential is continuous at the interface. Okay, so that's one conclusion we get from Faraday's law. Now we could do this for the Ampere-Maxwell law to see what happens to the B field. It's a very similar thing. We could again think about an interface like this, and think about some little area like that. I'm not going to do it every step of the math. Again, we'll just get the idea. Since we're working inside of a material, we have to write Ampere Maxwell as H dot dl. Right, and then as we go around the loop of H dot dl, that would be the ddt with the free currents, but we're assuming no free currents. But then it would still have a time rate of change term of the displacement field, which we talked about with polarization was just epsilon naught E plus the P field dA. So if you've done electromagnetism in materials, that's one thing that you might get. But it turns out to be the exact same situation. What we're going to do is shrink delta y to 0. And we can still call this L. Okay? So whatever you put in here doesn't matter. It's going to 0. The dA is going to 0. That part's going to 0. We have, again, this case that the H, the magnitude of H times L, just the tangential outside magnitude of H times L equals the tangential inside magnitude of H times L. So we find that H is continuous across the boundary. But what is H? H, in this case, if we had two different magnetic permeabilities, mu1 and mu2, then we would know that that's really just B, the real magnetic field you're used to thinking about, over mu1 equals B over mu2 because H equals B over mu. All right? And for dielectrics, all the mu's are basically the same. Right? Mu, the relative permeability, it's basically 1. Right? So mu1 equals mu2. So really, what this is telling us, the fact that the H field, the H magnetic intensity is continuous, is that the tangential B field is continuous, just like the E field. So all we need to move forward with Maxwell's equations, or to move forward to calculate the Fresnel equations, is that the tangential components of E and B are continuous at the boundary. It's absolutely true here, and it's pretty much true here for dielectrics, assuming that they have no interesting magnetic properties. This is just Maxwell's equations. I can give you a teeny bit of intuition for this, not a huge amount. For instance, if we think about the electric field, and you think about what's going to happen at a boundary. Right? So this is a dielectric boundary. And we know it's neutral, and it's got lots of charge, but all the charge is covering each other up. So what if we apply just some E field to this boundary? We know that it would push the positive charges here away from the negative charge there. Right? And here, it would push the positive charge away from the negative charge, and the positive charge away from the negative charge, and the positive charge away from the negative charge. Right? So it would kind of be, tethered like that. Those molecules would push. And we know that the material would still stay neutral because some other positive would get pushed up here. Right? So when you learn about fields and materials, you learn you get a real charge at the surface. It really, really does happen. But the point is that for this infinite plane, the charge can only show up on the surface, and that can't have a direction. Right? So really, you don't really see that the charge went this way to show up on the plane, because that looks the same if it went this way or this way. All that happens is, even if you apply a field perpendicular, all that happens is the charge goes up this way. If the charge goes up that way, you get a surface charge here, and what field is created by the surface charge? A field like that. A thin sheet of charge just makes a field normal. So really, even if you apply the field at an angle, the motion or the new charge that shows up only creates a field this way, so it only messes with the perpendicular component. The tangential component doesn't get altered. Okay, so that's a non-mathematical, hand-wavy way to think about it, if you'd rather do that. Or if you'd rather just believe in Maxwell's equations, you can go with this.